Hi, this is David. Welcome to a video review for Stock and Watson's Introduction to Econometrics. You may be using the brief edition, but in either case, this is Chapter 7, which is Hypothesis Tests and Confidence Intervals in a Multiple Regression. So we've moved from a univariate regression in earlier chapters now to the more realistic case of a multiple regression or multivariate regression, where we have multiple regressors, or what I prefer to call multiple independent variables. In terms of the learning objectives that GARP has assigned, we have the following. These first two look similar, except the difference is a single coefficient and multiple coefficients. So this first learning objective asks us to construct, apply, and interpret hypothesis tests and confidence intervals for a single coefficient in a multiple regression. And then the second one is for multiple coefficients in a multiple regression. We will see also the F statistic, which is a new concept in the regression, and that's because we're now in the multivariate regression. In the univariate regression, the F statistic didn't really have an application, but now we need it to test a joint hypothesis. Then we have interpret tests of single restrictions involving multiple coefficients. So we're going to see this idea of restrictions comes into play, and then we have confidence sets and examples of omitted variable bias, which we did see in the previous video, or this concept of omitted variable bias. The omitted variable bias, you may recall, was a likely reality in the case of a univariate regression where we're only regressing against one independent variable. If we think about it, there's a good probability that we have omitted some variable. And then finally, the R squared, or coefficient of determination, and the adjusted R squared becomes important in the multiple regression. And so the first learning objective is construct, apply, and interpret hypothesis tests and confidence intervals for a single coefficient in a multiple regression. And so we have a theoretical assumption that the ordinary least squared estimator has a normal distribution which its mean, or its expected mean, is the population mean, and a variance that we can estimate consistently. So as a first step, the standard deviation of any single coefficient, or OLS estimator, which is denoted here generically with the B caret sub j, of the jth regression coefficient, is estimated by its standard error. And so this is not really new. The notation has just been generalized, but we've always said that the standard error is a standard deviation. So if we have the estimator here, and this is an estimator for a partial slope coefficient in the case of a multiple regression, then what we care about is its standard error, the standard error of this estimator for a partial slope coefficient. And as before, this is the same pattern. We typically test the null hypothesis that the regression coefficient, the true regression coefficient, is equal to some specified value. And we compute the test statistic, which Stock and Watson denote here, the test statistic as T, and then it's a superscript ACT, ACT, meaning test actual. And so I hope this format is, this formula is familiar, right? If it's the regression coefficient minus the null hypothesis. This came up in the forum just last week, seeking clarification on this. So, I skipped a page. By accidentally hitting the page. This came up in the forum, so it's always, I think requires some practice to get handy with this, but this is the way we want to do it. Somebody asked if these could be swapped, but I think we should stick with the format that we're given here. And just if we look at this symbolically, we have a regression coefficient. The way that I think about this is that is the partial slope coefficient that we observe in the regression. We run the regression, we get a value, and we're going to subtract the null hypothesized value, which in many cases, the default, so to speak, is going to be a 0. But that's the difference between what we observed and what we hypothesized for the null value. But that's a difference in raw units, is it not? So we divide by the standard error, which is a standard deviation, to standardize this in much the same way in that what we'd standardized into a z value with a normal distribution. So we're computing this distance between the observed and the hypothesis value into standard units. Except that in this case, it doesn't have a normal distribution. It's a student's t distribution,